In this section, we're going to look at the thermodynamics of phase changes. Before we get into that, we're going to do a little review and look at the thermodynamics that take place whenever a substance changes temperature. So in order to do phase changes, we're going to have to be able to heat up and cool down specific substances. So we've already looked at this in the first semester of general chemistry as part of thermodynamics, and we have this equation that says that the amount of heat to cause a substance to change temperature follows this equation. So Q is equal to mc delta T, where Q is the heat change in joules. So mainly what we're going to be looking at is the heat change that occurs in changing phases and changing the temperature in different substances. M is going to be the mass and substance of the substance in grams. Delta T is the change in temperature in degrees C, T final minus T initial. And C is the specific heat of the substance in joules per gram degree C. And one of the things you want to pay attention to here is that the specific heat of substances changes as the phase changes. So we'll take a look at that here in just a second. So that's when temperature is changing, but when we actually go through a phase change, the temperature does not change. So some heat changes do not involve a temperature change. These are called isothermal. And that's what happens whenever we do a phase change. So during a phase change, so say going from a solid to a liquid, the temperature doesn't change, but there's still a change in the amount of heat that's going on. So it's isothermal. The temperature doesn't change, but there's still heat being moved around, and that's what we're going to be looking at here. And that's what happens whenever we undergo a phase change of a substance. In this case, we're going to look at the amount of heat that is involved in the change of the state of a substance, just like we did with a reaction. So we're going to use an enthalpy, and it's going to involve Q reaction. So we're going to be looking at a heat of reaction. We're going to call that reaction the change in our substance. So this is this change of heat in between the system or our surroundings. And really what we're going to be looking at is the enthalpy of reaction. So we're going to be using this to look at the enthalpy of phase changes. So in this case, delta H is in joules per mole, and sometimes it's going to be in kilojoules per mole. So that's something else that you're going to have to watch out, because a lot of the times enthalpies are in kilojoules per mole and specific heats are in joules per mole. So we're going to have to make sure that our units are in alignment. So the basic equation for enthalpy is that delta H, the enthalpy, is equal to the Q of the reaction divided by mole of reactant. And in this case, our reaction is going to be the phase change. And overall, what we're going to be looking at is the amount of heat being absorbed or given off during a specific phase change. So the variation of this equation that we're going to be looking at Q reaction. So enthalpy times mole of reactant is going to give us our Q of reaction. So just like reactions, phase changes can be endothermic or exothermic, and we'll be taking a look at that. A lot of this is kind of intuitional. You should be able to figure this out. But remember, by definition, exothermic means delta H is a negative number, and this is going to mean that Q reaction is also going to be negative. And overall, this means that the phase change is going to be giving off heat to the surroundings. The exact opposite is true for endothermic reactions, so that delta H is a positive number, and this is going to correspondingly mean that Q reaction is going to be positive, and this means that the reaction absorbs heat from the surroundings. So a lot of the times, just by looking at the actual phase transition that we're going to be undergoing, you can kind of intuitively know, is it going to take heat, or are we going to have to remove heat from it to cause the phase change to occur? So let's look at some of the major phase changes that we're going to be looking at here in this chapter. So the first one's called the melting point, and that's when we undergo the phase change of solids turning into liquids. So this makes sense that it's going to be endothermic. So if I want to melt something, I got to put heat into it. And we do have an enthalpy for it, and we have a specific enthalpy. So here, this is something else that you got to pay attention to, is that the enthalpy for different phase changes are going to be different. So you have to be very specific about what phase change you're looking at. So the enthalpy for the melting point is called delta Hfusion. And here now, when we look at the freezing point, we're kind of flipping things around. Now we're going from liquids to solids. Instead of endothermic, this is going to be exothermic. So in order to freeze something, I need to pull heat away from it. That makes sense. And what they do here, instead of calling this a different enthalpy, they just put a negative sign on there. So it's still delta H of fusion, they just put a negative sign. So the actual number is the same. What changes is the sign, depending on which direction we're going. So this negative sign here is going to be very, very important, and we're going to see this again later on when we do some calculations. So another phase change that occurs is sublimation. This is when solids goes into gases. This is endothermic, and it's got the enthalpy delta H of sublimation. And the opposite of this is called deposition. So this is something many people have not seen. It's when a gas goes into a solid directly. So it's the exact opposite of sublimation. This is exothermic, and it's going to be negative or delta H of sublimation. Boiling point, same thing. Liquids going into gases. So if I want to boil something, I got to put heat into it. So this is endothermic. We got a delta H of vaporization. And the opposite of this is condensation. So that's when gases turn into liquids. In order to do that, we need it to be exothermic, and so now this is negative delta H of vaporization. So there's three different major phase changes that we're going to be looking at in this chapter, and it's really this negative sign. You really need to say, which direction am I going? Does it make sense? Am I putting heat in, or am I taking heat out to cause this phase transition? So one last thing we want to look at, it's not necessarily a phase change, heats of solvation. So whenever I mix two things together, if I put a solid into a liquid, or if I mix two liquids together, often there is a enthalpy involved with that. So mixing a solute and a solvent to form a solution is like a phase change, and there's actually a delta H of solvation involved with this. And this can be actually quite a bit, and as you get along in chemistry, this can have a pretty important effect on some of the things you're doing. You can't just mix two things together without heat being absorbed or given off. The strange thing about delta H of solvation, it really gets into the liquids and maybe the solids that you're playing around with. It can be endo or exothermic depending on what you're playing around with. But there is, and this is something you want to keep in the back of your brain, whenever you mix two things together, there is going to be some type of heat change. It may be so small that you don't see it, but trust me, sometimes it's large enough to have an effect on whatever you're doing. Now that we understand a little bit about the thermodynamics of phase changes, let's look at some examples. And one of the things you want to remember while we're looking at these examples, you want to constantly be thinking, is the specific thing that I'm looking at involving a change in temperature or not? And so when we say it's not involving a change in temperature, remember that's isothermal. That happens when we're just changing a phase. So I always want to be thinking that, am I talking about something where the temperature is changing because that uses the Q is equal to MC delta T equation, or am I talking about something where the temperature is not changing because that uses delta H times mole of reactant to give us our Q of reaction? So our first example here is probably the simplest. I say I have 60.1 grams of ice and I want to turn it into liquid water. And here you can tell I'm not talking about a change in temperature because I've given you no temperature information. Really, this is just a phase change. I'm going from solid water to liquid water. In this case, I need to give you the delta H of fusion for the water, which is here. And remember, the units on the delta H, or the enthalpy of fusion, is kilojoules per mole of reactant. So my reactant now is the ice. So what I need first is the number of moles of ice. So I have 60.1 grams. The molecular weight of water is 18.02 grams per mole. So overall I have 3.34 moles of water. And I know for the change of a phase, it's to get to Q of the reaction, and that's really what we're asking here, is how much heat is required to do this. It's delta H of fusion times the moles of the substance. So delta H of fusion is given here, moles of substance we found, we multiply the two together, and my answer is going to be 20.1 kilojoules. So one of the things that you always want to take a second and check is, does my answer make sense? So with a Q being positive, that means that this reaction should be endothermic, and that makes sense. In order to make ice to melt into liquid water, I need to be putting heat into it, so it makes sense that my Q is a positive number. So with this next example, we're taking it up a little tiny bit. And this is where it starts getting tricky, because one of the things you got to remember is whenever we do a phase change, that phase change happens at a specific temperature. The other thing you got to remember is that the specific heat of different phases are different, so we have to treat them differently. So when I look at this, I say how much heat must be absorbed to turn 10 grams of ice at negative 15 degrees C into liquid water at 25 degrees C. One of the first things I notice is I'm talking about changes in temperature. So changes in temperature means that we're going to be using our Q is equal to MC delta T equation. And the other thing I want to know is at some point inside of here, I'm going to be undergoing a phase change. I'm going from ice, which is solid water, to liquid water. And I got to remember that that happens at a specific point. So hopefully you guys all remember that ice melts at 0 degrees C. And so I need to first warm up my ice, which is at negative 15 degrees C, to 0 degrees C. And then I need to turn it into liquid water. And then once I turn it into liquid water, I can continue on warming this up to 25 degrees C. So we'll see this a little bit better here in just a second. One of the things I really want to pay attention to, we have two different phases here. So the change in temperature of ice is going to use one specific heat, and the change in temperature of water is going to involve another specific heat. So I need to treat those two pieces differently, and we'll show how we separate it out here in just a second. Also, we're undergoing the phase change in between a solid into a liquid, so I know I'm going to be needing dHofusion, which is given here. And with this, the two pieces I need, so I need to know how much ice I have. One of the first things I want to do is convert that into moles of ice, so it's just grams divided by our molecular weight of water, which is 18 grams per mole. So we know how many moles of ice that we have. So now let's look at how all this comes together. I know that I have two different phases. I've told that I have ice, which is a solid, and liquid water, which is a liquid. And I know somewhere inside of there I'm going to need to have a phase change. That phase change is a different equation than the pieces where I need to heat it up. I know that this phase change happens at 0 degrees C. So the first thing I need to do is heat up my ice to 0 degrees C. So there's going to be one piece here that's involving a change in temperature, so I'm going to be using the Q is equal to MC delta T equation. The phase change, enthalpy of fusion times mole of reactant, and then once I convert the solid into a liquid, I then take that water, which is going to be at 0 degrees C, and continue to heat it up to 25 degrees C. Here we're talking about a change in temperature, so I'm also going to be using the Q is equal to MC delta T equation. So notice during this whole time while we're converting a solid into the liquid, the temperature actually doesn't change. It stays at 0. I can't heat up my situation past 0 degrees C until all of my ice is gone. So there's actually three different pieces to this equation, and part of this is because we're doing a phase change. Another part of this is because we're changing temperatures, and that change in temperature part is broken into two pieces because the specific heat of ice and water are going to be different. So I have three different pieces, so I like to set it up like this and say what's going on in each piece, which equation do I need to use. So changing in the temperature of the ice, that's my MC delta T. So I have 10 grams of ice, the specific heat of ice. So I want to make sure I'm using the right specific heat here. So the specific heat of ice is different than the specific heat of liquid water. And then I say, what's my change in temperature? Delta T is T final, so I'm going to 0 degrees C, minus T initial. So my initial temperature was 15 degrees C. Once I get there, I have to convert my ice into liquid water. So that is my enthalpy of fusion. So that was given. And then note here, a lot of the times the enthalpy of fusion is given in kilojoules per mole. Well, the specific heats are given in joules per gram degree C, so typically we convert these kilojoules into joules, and I do that just by taking the number and multiplying by 10 to the third. But I got to make sure I have the right units. The units need to all be the same. So this piece, enthalpy of fusion times mole of my reactant, so my reactant's water, so we found the number of moles here. And then once I'm done with that, all I have to do is heat the water up from 0 degrees C to 25 degrees C. So we're still dealing with 10 grams, of my water. Now the specific heat of the liquid water is different, so I need to plug that in. T final is 25 degrees, and T initial is 0 degrees C. So a couple of things you want to watch out for. So easily the most common mistake I see on exams about this is where people do not plug in the temperatures into two different equations. Typically they will get the enthalpy part, and then they'll have one MC delta T equation, and they'll say my end temperature is 25, my initial temperature is minus 15, and that will be delta T. Well, that's wrong. I can't do that because I'm dealing with two different phases. So that is the main mistake I see people doing, is they'll just say, this is my final temperature, this is my initial temperature, I find delta T and I plug it into one, and I pick one specific heat or the other. So that's wrong. The other thing you want to do is, and we'll see this in the next example a little bit better, it's very tricky to make sure your signs are going the right way. And one of the things that I do at the end, I check the signs on everything. So when I'm done, I specifically calculate each of these three pieces. The sign on each piece of the overall total, so the sign on each answer from each individual piece of this overall equation must have the same sign. I can't be going in one direction and the other. This whole time it needs to be going in the same direction. So if I have like a positive, a negative, and a positive, I've done something wrong. And that's something that you can always check at, and it's a really good way of catching your answer. The last thing I do, so I've gotten the numbers from each one of these individual pieces, I add them all up, I get the total amount of heat that causes this phase change, and then I take a second and say, does this make empirical sense? My Q total is a positive number, and yeah, taking ice and melting it and turning it into warm water, I got to put heat into it, so it makes sense that my Q total is a positive number. So let's look at one more. This one's a little bit trickier because now we're going to be going in a different direction, and so this is where that negative sign that I was talking about with the enthalpies of phase changes show up, and we'll talk about how we know to be able to catch this. So now I'm taking 2.5 grams of steam, so we're talking about gaseous water. It's initially at 115 degrees C, and I say I'm turning it into liquid water. So here I'm giving you the specific heat of steam, which once again it's different. So each phase of water has a different specific heat, but now our phase change is going from a gas to a liquid, so we're going to be using delta H of vaporization. So that's given here. And as always, because we're going to be using delta H, one of the first things I want to do is find out how many moles of reactant or how many moles of water I have. So that's 2.5 grams divided by our 18 grams per mole for water. That gives me 0.139 moles of water. Then I take a second and look. The two questions that I have, do I involve a phase change? Yes, I'm going from a gaseous water to liquid water, so I know I'm going to be using the delta H times molar reactant equation. Do I involve a change in temperature? And so once again, this gets a little tricky. With water, you should know that the phase change from liquid going to steam and steam going to the liquid occurs at 100 degrees C. So if it's something other than water, you'll either have to find the boiling point or it should be given to you. But I know I'm going to have to involve a change in temperature because this phase change occurs at 100 degrees C, and I've told you that I'm starting with steam at 115 degrees C. So in order to cause this phase change, the first thing I need to do is take my steam and cool it down to 100 degrees C. Then once I do that, then I can convert my gaseous water steam into liquid water. So there's actually two pieces to this equation. One where I cool down the steam to 100 degrees C, and then here where I convert my steam into liquid water. So this is the tricky part. I need this negative sign in there. So for converting the steam into liquid water, I'm going to be using delta H of vaporization times the mole of the water, but it's up to me to know that I need to put a negative sign in there. If I am going towards an exothermic phase change, by that I need to pull energy out, and I know I'm doing that. In order to turn steam into liquid water, I need to pull energy out. I need to show that energy is leaving the system by putting a negative sign in here. So remember, it's up to you to know when to put this negative sign into this equation. But what's nice is we'll have a fail-safe here where we can double check our answers, so you can kind of go back through and see if you forgot to put this negative sign. So the two pieces to cool my steam at 150 degrees, 15 degrees C into liquid water, MC delta T. M is the mass of my water. C is the specific heat of steam, which was given here. My final temperature was 100 degrees C. So that was something that I needed to come up with. Either I just knew, because we're talking about water, this phase change happens at 100 degrees C, or I could have been given the boiling point of some other liquid, but it was up to me to come up with this number. And so it's T final minus T initial. My T initial was given here 115 degrees C. Also, the other piece, so doing the phase change, so between the gaseous water into liquid water, that's going to involve negative delta H of vaporization times mole. And here again, enthalpies of reaction or phase changes are typically given in kilojoules. So I got to remember, I got to convert my kilojoules into joules. How I do that is I just take my number and multiply by 10 to the third. It's delta H times mole of my reactant here. So my reactant is water, so we calculated that here. And I get my two different pieces. When I look at this now, I use the fact that the sign on both pieces inside of my overall calculation need to have the same sign. So if this part's negative, this part needs to be negative. And that's something that I can use to check, did I forget to put this negative sign up here? That's how you check it. So remember, no matter how many pieces of an equation that I have, the sign on each individual answer from this overall equation must have the same sign. So here I do the calculation, I get the total heat change inside of this change to be negative 6.19 times 10 to the third joules. As always, I take a second and I say, does this answer make sense? Yeah, so if we're going to take steam and cool it down into liquid water, that's an exothermic process, so I need to be pulling heat away from it. And so that means the sign on my Q total makes sense. So if it's exothermic, I want a negative sign there.